Okay, welcome to the last session of the day. It seems we can start. So we're happy to start with Susha telling us about her last de Sitter work.
Okay, hello everyone. You can hear me, I think, right? Yes? So indeed, I will be talking about Transient de Sitter Vacua from interacting dark sectors. This is work done in collaboration with Ed Hardy and our student Joaquim Gomez. And I also can't resist mentioning very briefly some work by my very excellent student Marco, who is somewhere in the room, that relates to some of our discussions from yesterday. Oh, sorry, I should. Okay. So, as we all know, runaway moduli are, of course, ubiquitous in string compactifications, but despite lots of recent effort, it seems that they always seem to be too steep to source quintessence. Perhaps this is not so surprising. If we were to be having some accelerated expansion in the asymptotically along these runaway directions, we'd have to deal with time variation of fundamental constants unobserved, fifth forces, and we'd have to face the question, if we have eternally accelerated expansion that leads to cosmological event horizons, we'd have to face the question of how to formulate quantum physics in the presence of these event horizons. All that is to say that it's probably fair to say that metastable de Sitter Vacua via quantum effects, probably with numerical control, with some anthropics to explain the cosmological constant problem, is probably still our best explanation of dark energy, and I'm afraid that won't really change at the end of the talk. But still, I guess we all agree that it's important to think about possible alternatives. So let me mention just a couple before getting into the main part of the talk, a couple of ideas that I think are interesting. So there's been this work recently by Dimitros and others who have found that one can actually obtain asymptotic accelerated expansion from steep runaway directions if the space-time, the 4D space-time, has negative spatial curvature, so an open universe, and that's precisely in that case, the event horizon, the position of the event horizon goes off to infinity. So it seems like an interesting observation. The big question, of course, is how relevant that might be for cosmological observations, and that's something that we're thinking about now. Another direction that seems, of course, important to study is the relatively unexplored area of string theory, which is non-supersymmetric strings. Will these offer an alternative place to search for accelerating solutions? So far, it seems that we just find more no-go theorems, and here I just mentioned these results from Marco, considering type 2 compactifications with some maximally symmetric space-time times another maximally symmetric space times a Schurz-Schwarz orbifold, so breaking supersymmetry with the Schurz-Schwarzing, with fluxes which can be tadpole free, and potentially curvature from this space here. So the SUSY breaking and gives rise to Casimir energies, as we've heard just now from Bruno, potentially a way to evade the Maldacena-Nunez, but unfortunately we seem to find still no de Sitter solutions. As an aside, this setup does lend itself to finding non-supersymmetric ADS with parametric control. They're scale separated, only partially scale separated. Yosif will tell us that we're cheating, but okay, they've been found, these non-SUSY solutions. Unfortunately, we haven't yet exhausted all the possibilities, but it seems like they all seem to be tachyonic. below the BF bound. But I should mention, Alessandra was telling me in the coffee break this morning, and it came up in some of the questions, there's earlier work finding non-SUSY ADS vacua, which are at least perturbatively stable, which I'm sorry they're not in my reference list, including Alessandro and Gaiotto. Okay, so that was just some general motivation. So this is a real part of the talk, my plans. So I'll be talking about string-inspired, shall we say, mechanisms to dynamically stabilize steep runaway directions into a transient de sitter vacuum. This can be done consistently with cosmological observations and consistently with the swampland conjectures. And so this is how I'll present to you those results. So I'll present the idea how interacting dark sectors can lead to the transient de sitter vacuum. I'll show you that despite the Lagrangian potential having no de sitter vacuum. And then I want to point out the observational constraints. I'll mention some the fine-tuning, the status of the fine-tuning in the scenario, the swampland conjectures, and then I'll give you some outlook. And of course, a very important part of that outlook is an embedding into string theory, which we're only really just beginning to think about. Okay, so this is so I have to apologize that there's not much string theory in this talk. The talk will focus on the dark matter, dark energy scenarios. I won't have time to discuss, but you can look into the paper if you're interested. Other parameter spaces are also possible with dark radiation, kind of helping to get dark energy, and also multi-field quintessence scenarios. And another thing I will not discuss is the cosmological constant problem, I'm afraid. Okay. So here's the idea. So we'll just have a simple toy model, which kind of from which you can see all the physics and get the intuition. So just two interacting hidden sector scalar fields with canonical kinetic terms and potential energy functional. The potential energy functional will take this form. So this is my field psi will play the role of the dark matter. It has a mass term. My field phi will play the role of the dark energy. And I'll just assume that it has kind of a Higgs-like hilltop potential with a de sitter maximum, or a steep runaway potential. Exponential runaway, and for the talk I'll be focusing on that steep runaway. And key is that there will be this quartic interaction term between the dark matter field psi and the dark energy field phi. Now, without that interaction term, so I'm parameterizing. I have these parameters here, lambda, which is kind of giving the field range of my field phi, so it's somewhere below m Planck. And my quartic coupling are right in this way in terms of a mass scale m int over lambda, the field range of phi. And when the quartic coupling goes to 0, is equal to 0, either phi or psi could source a slowly rolling quintessence, but of course only by fine-tuning the initial conditions, say to the top of the hilltop, or with phi rolling first up its exponential potential and then down. Or with some dangerous large field distances. And what I'll show you now is that when the quartic interaction term is non-vanishing, with psi behaving either as dark matter, dark radiation, or some subdominant dark energy component, this psi can dynamically stabilize phi near to phi is equal to 0, where it can source our observed dark energy in a transient de sitter vacua. So here's the mechanism for dark matter. So let's just assume, to begin with, some Friedmann-Robinson-Walker background. There's the energy density, which I'll assume is dominated by this contribution to the potential energy from my field phi. This is, we can solve numerically the full cosmology, which we'll do below, but just to get the intuitive picture. we'll make this assumption that the dynamics of psi is dominated by its mass term, just so that the dynamics is linear, things are simple. Of course, psi just obeys its Klein-Gordon equation in a FRW background. If psi starts away from its minimum, so somewhere up its quadratic potential, anywhere really, up its quadratic potential, and psi has a mass which is greater than the Hubble constant today, then it will, at some point in the history of the universe, it will begin to oscillate in its quadratic potential. This is its solution. So it has these oscillations, which you can think of as a collection of scalar particles oscillating coherently with the frequency set by the mass, and the energy density in these oscillations evolves as matter. Okay, so supposing that the oscillations are the oscillations here are fast enough that we can just average over them, then the quartic interaction term in the Lagrangian in this background of psi sources an effective mass contribution for phi. You can solve then the equation of motion for phi, or as a first instance, just find whether its effective Lagrangian potential has a minimum, and indeed it does. This is the minimum of the potential for effective potential for phi in the background of psi. That's the principal branch of the Lambert function, the special function, and so we see that phi can be held in a de Sitter minimum where it sources dark energy. Okay, so that's kind of the very simple picture. The minimum for phi, again, it takes this form. It depends on the average of the oscillating dark matter field. The solution exists for any value for psi squared. But remember that even if we average over the oscillations, the amplitude of the oscillations is, of course, decaying because of the Hubble friction. That leads to a time dependence in the de Sitter minimum. And if we want to satisfy observational constraints that the dark energy does not evolve too much, this ends up giving a bound on an upper bound on the number of e-folds of accelerated expansion that one can obtain. We can do a bit better than that as well, so we can kind of think about the full dynamics of phi in this oscillating background of psi. Roughly speaking, phi obeys a mature equation with there's a second order ordinary differential equation with an oscillating stiffness coefficient, which is coming from those oscillations in psi. The coefficients of the in the mature equation are time dependent. This might be familiar to some of you who have looked at preheating, this is parametric resonance. Okay, and there's the solutions to this mature equation are well known, and they take this form. And what we learn from all of this story is that phi in general, so our dark energy field in general can undergo a parametric resonance instability, so away from its minimum due to this coupled behavior between the phi and the psi, which would end the dark energy domination. We can evade that by ensuring that the Hubble friction is enough to suppress this growing mode, and that puts upper bound on the mass of psi ultimately. So right, so m psi has to be less than around 15, the Hubble constant today. At late times, so the amplitude of the oscillations of psi are getting lower and lower. At some point, it will its influence will drop out and will effectively go to the exponential runaway again, and the solution will so the phi will then go to a global attractor, non-accelerating scaling solution down at steep runaway potential, which is well known, in which the energy density remains a fixed small fraction of the total energy. So it's a kind of transient de Sitter, which and the final endpoint is a non-accelerating scaling solution. Okay, so that's kind of the general intuition. One can then just go ahead and check all those ideas by solving numerically the equations of motion. The parametric resonance condition that it must not end, the parametric resonance must not end the dark energy E-block too quickly. Remember that put an upper bound on the mass of psi. That means that psi will kind of begin its oscillations. It will get unfrozen by the Hubble. I mean, you know, it will start off. It's a light field. It will start off being frozen by the Hubble friction. At some point, as H falls, psi begins to oscillate. But that will, because psi is so light, that will happen well after matter radiation equality, and that what that means is that psi cannot be all the dark matter. So when we're solving the full cosmology, we'll put in kind of an additional contribution of dark matter, which is the dark matter that we observe. This is just one example of a solution, like some parameters which reproduce our cosmology, the lambda CDM model. So this is, I don't know how visible that is to everyone. This is the equation of state parameter with respect to the scale factor, and we match the equation of state parameter of lambda CDM up to some point. Actually, it's around 0.5 e-folds after today, when then we go to the effectively a matter domination. And how much time do I have?
Still have 8 minutes.
Okay, great. So and so this is what's happening to the field. So psi is slightly lighter than phi. At early times, we've just kind of imagined that, you know, something like inflation sets up the initial conditions, and both fields are starting somewhere away from their minimum as the universe cools and H falls. First of all, phi will be unfrozen from its minimum, and it will start to oscillate around its effective de Sitter minima. Pretty soon it will start behaving as dark energy as the amplitude of the oscillations fall, and then later psi will also start rolling and behave as a subdominant dark matter component. During that kind of complicated coupled behavior, phi effectively gets locked near to its minimum, and then finally the amplitude of the psi oscillations gets so small that phi begins to roll off down its exponential runaway. So the upshot is that we can get cosmologically viable models with no fine-tuning of the initial conditions. There's no super Planckian distances. All the field ranges are sub-Planckian. There's no fine-tuning between the Lagrangian parameters, and it's consistent with the cosmological observations. So there are potential observable signals. We have this component of dark matter, extremely light dark matter, for which there are bounds, and whose bounds will improve with future CMB observations and the square kilometer array measurements. Potentially we can have variation of the equation of state parameter of dark energy if we're, near around the bounds of parameter space. There could be some spatial variation in the equation of state parameter depending on how the initial conditions are set up for our dark matter field, and as I'll speak a bit more about that, there are forces as a result of these extremely light fields. So here's our parameter space, which is allowed, and I think there's not too much I want to say, just if that again, I'm not sure how visible that is. There's our upper bound on the mass of psi to avoid too early parametric resonance, which would take us away from the dark energy epoch. If the mass of psi is too light, you just get to a quintessence limit, which is maybe less interesting. There are some bounds kind of require, that the coupled behavior doesn't lead to too big oscillations in phi, while psi is oscillating, which would kind of lead to too much variation in the dark energy. Okay. So I should make some comments on the fine tuning in the scenario, in particular kind of thinking about what one might hope for from a UV complete model. So we need light scalar fields. In fact, all the scales in the problem are set around H0, and that's similar to quintessence, and comes with the problems that quintessence models have. So there's one good thing is that at least this quartic interaction, so the quartic interaction itself has to be small for the mechanism to work. The quartic interaction, of course, itself would lead to UV sensitive contributions to the masses of psi and phi, so there'll be loop corrections to the masses of psi and phi due to that quartic interaction, and that at least does not require too much fine tuning, so there'll be sufficient, the loop corrections are sufficiently suppressed provided that the UV cutoff is not too far from the Planck scale or from lambda. There'll also be corrections from gravitational couplings to visible sector states, say with mass m, and there we would require some fine tuning for any states that are for the states that are less than greater than, say, GeV, and there'll also be corrections from heavy string states, and all of this is, of course, these last 2 points are similar to quintessence, and one can, aim to do some model building. Perhaps sequestered SUSY can help with these issues. Before closing, let me just, some of us might want to check, is the scenario consistent with the swamp-Planck conjectures? As I already emphasized, all the field ranges are some Planckian, so there's no kind of worry about control of the effective field theory from that point of view. The de Sitter swampland conjecture can be satisfied for some ranges and windows of parameter space. One can check that analytically, kind of for the whole field range of psi and along the minimum for phi, and one can then just check numerically that the swampland conjecture is satisfied for the full cosmological trajectory, and because we just have a few e-folds of accelerated expansion, the transplanckian censorship conjecture is also satisfied. So let me end with some outlook. As I've said, a light hidden dark matter scalar with a mass kind of around Hubble scale, slightly bigger than Hubble scale, can stabilize a steep runaway modulus in a transient de Sitter vacuum via this quartic coupling with our dark energy field, which also has a mass not much bigger than H0. we can get a natural cosmological history without fine-tuning of the initial conditions or super-Planckian field distances. So in that sense, it does somewhat better than kind of vanilla quintessence models. And there's only a transient de Sitter epoch, so we don't have to worry about eternal acceleration, cosmological horizons, and the EFT seems to be consistent with the swampland conjectures. The UV sensitivity from the quartic coupling, which is key to the scenario, that UV sensitivity is mild, though you need some sequestering from the visible sector to suppress fifth forces. It's not much difference from quintessence. One can wonder if axions would play a role in helping there. And other parameter spaces are possible, with psi playing the role of dark radiation or multi-field quintessence scenario. Maybe one thing that's worth pointing out is that for the dark radiation, the scales are different, and like the masses and the coupling scales are fixed by rho dark energy, so by around milli-electron volts rather than 10 to the minus 33 electron volts. Embedding into string theory would of course be interesting, and in particular because we have these light scalar fields and we have to avoid the fifth forces, we'll have to think about, that whatever the fields are, they have to be some kind of local moduli rather than volume moduli or the dilaton or whatever to be able to sequester from the visible sector. Okay, and I will leave it there.
We have time for questions. Yes.
Very nice, Susha. Great. Any hints about your work in progress on string?
Well, I'd be very happy to hear if any of you guys have ideas. We're really just beginning to think about it. So it's true, of course. So I wanted to emphasize kind of the steep runaway thing. But if we were to start with the hilltop, for example, instead, then that's just the same Lagrangian that's the hybrid inflation Lagrangian, and there have been attempts at string embedding of hybrid inflation with D-branes and so on. So that's and that would provide us also with the local aspect, very characteristic of the fields that we need. So I think that's probably the first thing to think about is that it needs to be local, and we do. Maybe one thing that's quite tricky is that so it doesn't necessarily need to be a quartic coupling. It just needs to be a coupling, that has the right kind of shape, the bit that's in the right direction. So maybe I'll continue. Otherwise, I'll just babble. I'll continue after.
And any attempt to do this early dark energy using this?
Yeah, that's a really good question, and also that's also really nice because then if you exit after the exit of early dark energy, there could be hope for proper signals. So that is a really nice question. So after we had like this thermal dark energy scenario, which was kind of the dark radiation version of this. There have been some works in kind of that, in using that kind of scenario for early dark energy by Martin Sloth and others, and I think actually they've done quite a lot in that direction, which is interesting.
When this equation of state parameter goes to -1, that's, I guess, when you want to be today, right?
Exactly, yeah.
And that is kind of a why now problem, isn't it? I mean, you need to do something to make that happen.
Is it a why now? I mean, so in some sense, it's nice that it's fairly independent of our initial conditions, that we do end up independently of the initial conditions, as long as you're starting somewhere away from the minima, right, which is like the generic thing that you'd expect, then you get to this de Sitter vacuum. And then I guess it's just a question of, I mean, we're not explaining why the rho dark energy is the same order of magnitude as the matter. That's true.
Okay.
And that's, I guess, in particular because the scales didn't work, right? Because we needed our mass of the dark matter to be super light, so it couldn't be all the dark matter, and so I think we don't. That's true.
Yeah, about the latter point. So, wouldn't you say that you somehow solve, on the one hand, the cosmic coincidence problem, and on the other hand, I would still say naively the cosmic constant problem, because in this scenario, the dark energy will always be of the same order as matter density, right? So, is it? Am I wrong?
I'd be very happy if you're right. I think I have to think about that. No, it was, to me, it did not seem that we're solving the dark, the coincidence problem, because, because I've put in the scales by hand. So
yeah, but you could say you put in the
no.
scales by hand, but the scales have to be consistent with what we observe. So dark matter the density should not be higher than the matter density we observe. So I don't know.
Maybe you're right. I need to think about it. Yeah. Thanks for the question. Yeah.
Thank you. I think it's time to move on, so thank you again for the nice talk.